Hello everyone. Today we are here to talk about the topic demand paging in operating systems. And this video is presented by GS Pradeep, register number 22B01A0544 and Kavya 22B01A0522 under the guidance of Dr. M. Prasad, PhD, Associate Professor, Department of CSE, SVCW, Bhimavaram. Optimizing memory management, unveiling the efficiency of demand paging. Coming to the topic introduction, in this presentation, we will explore the efficiency of demand paging and its impact on memory management. We will delve into the benefits and the challenges of this technique in optimizing system performance. This concept says that we should not load any pages into the main memory until we need them, or keep all pages in secondary memory until we need them. How can we understand demand paging? Now, let us see that. Demand paging is a memory management scheme that allows the system to retrieve data from secondary storage only when it is needed. This minimizes the need for extensive primary memory allocation and enhances overall system efficiency. Demand paging can be described as a memory management technique that is used in operating systems to improve memory usage and system performance. Demand paging is a technique used in virtual memory systems where pages enter main memory only when requested or needed by the CPU. In demand paging, the operating system loads only the necessary pages of a program into the memory at runtime instead of loading the entire program into memory at the start. In logical memory, in first place we have I, second place J, third place K, fourth place L, fifth place M, sixth place N, seventh place O, and eighth place P. In physical memory, in fourth frame we have M, and fifth frame we have I, and seventh frame we have P. According to this logical memory and physical memory, we write a page table. According to logical memory, first position is I. I in the physical memory we have in fifth frame. So that is valid bit. And in the fifth position we have M in logical memory. And in physical memory, it was in fourth frame. So we'll place it as valid bit. And in physical memory, P is available in seventh frame. So we place the seventh frame as valid bit. Remaining frames all are empty, so we kept the invalid bit in the page table. In this demand paging, we could bring entire process into memory at load time or bring a page into memory when it is needed. Less input output needed, no unnecessary input output. Less memory needed, faster response, more users. Similar to paging system with swapping, it is on the right side of the page. Page is needed, refer to it. Invalid reference abort, and if it is not in memory, bring to the memory. Lazy swapper. It never swaps a page into memory unless page will be needed. Swapper that deals with pages is a pager. In the figure, we observe that program A is swap out and program B is swap in. What is pure demand paging? We start executing a process with no pages in the memory. When the operating system sets the instruction pointer to the first pointer instruction of the process, which is on a non-memory resident page, the process immediately falls for the process. After this page is brought into the memory, the process continues to execute faulting as necessary until Every page that it needs is a memory. At this point, it can execute with no more faults. This is pure demand paging. What are benefits of demand paging? So, in the demand paging technique, there are some benefits that provide efficiency of the operating system. Number 1, efficiency use of physical memory. Number 2, support for larger programs. Number 3, faster program start. Number 4, reduce memory usage. Demand paging offers significant advantages, including reduced memory wastage, improved utilization, and enhanced system responsiveness. By dynamically loading data as needed, it optimizes resource allocation and enhances performance. What are challenges and considerations? While demand paging offers numerous benefits, it also presents challenges such as page faults. The process of swapping pages between memory and disk can cause a performance overhead, especially if the program frequently accesses pages that are not currently in memory. Increased input output operations and potential performance overhead. If a program frequently accesses pages that are not currently in memory, the system spends a lot of time swapping out pages, which degraded performance. Query paging can cause physical memory fragmentation, degraded system performance over time. Implementing query paging in an operating system can be complex, requiring complex algorithms and data structures to manage page tables and swap space. Understanding these considerations is crucial for effective implementation. Here, we see that steps in handling a page fault. 1. We check the internal table, usually kept with the process control block, for the process under consideration to determine whether the reference was valid or invalid memory access. Second point, if the reference was invalid, we terminate the process. If it was valid, but we have not yet brought in that page into memory, we now page in later. We find a page frame by taking one from the free frame list. For example, we schedule a disk operation to read the desired page into the newly allocated frame. Fifth point, when the disk read is complete, we modify the internal table kept with the process and the page table to indicate that the page is now in memory. We restart the instruction that was interpreted by the illegal address trap. The process can now access the page as it thought it had always been in the memory. In the figure, we observe that loadem is asking some page and it is not found in the page table. Then it forms a trap. Then operating system will check the page in the main memory and it brings in the missing page to physical memory. It plays in the free frame and reset the page table after placing that page, and the page table will given to the loadium. It restarts the instruction. Aspects of demand paging. Extreme case. Start process with no pages in memory. OS sets instruction pointer to first instruction of process. Non-memory resident is page fault. And for every other process pages on first axis, pure demand paging. Actually, a given instruction could access multiple pages, multiple page faults. Consider fetch and decode of instruction, which adds two numbers from memory and stores result back to memory. Pain decreased because of locality of reference. Hardware support needed for demand paging. Page table with valid or invalid bit. Secondary memory. Device with swap space. Instruction restart. Here is the demand paging example. Memory access time equal to 200 nanoseconds and average page fault service time equal to 8 milliseconds. If we have the formula EAT equal to 1 minus P into 200 plus P into 8 milliseconds, that is average page fault service time. 1 minus P into 200 plus P into 80 lakhs is equal to 200 plus P into 79 lakhs 99,800. So we can conclude that EAT is directly proportional to the page fault rate. How can we optimize in demand paging? To maximize the benefits of demand paging, it is essential to optimize page replacement algorithms. Adjust the size of the page file or swap space. Ensure sufficient physical memory to reduce page faults. Profile and optimize applications to minimize memory usage. Minimize page faults and carefully manage memory allocation. These strategies are crucial for achieving efficient memory utilization. Let us see advantages of demand paging. Only load pages that are demanded by the executing process. As there is more space in main memory, more processes can be loaded, reducing the context switching time, which utilizes large amount of resources. Less loading latency occurs at the program startup as less information is accessed from secondary storage and less information is brought into main memory. As main memory is expensive compared to secondary memory, this technique helps significantly reduce the bill of material cost in smartphones. For example, Symbian OS had this feature. Disadvantages of demand paging. Individual programs face extra latency when they access a page for the first time. Low cost, low power, embedded systems may not have a memory management unit that supports page replacement. Memory management with page replacement algorithms becomes slightly more complex. Possible security risks, including vulnerability to timing attacks, trashing, which may occur due to repeated page faults. Case studies and best practices. Exploring real world case studies and best practices in demand paging implementation provides valuable insights into effective memory optimization. Analyzing successful examples can offer practical guidance for system administrators and developers. What are future trends and innovations about demand paging? As technology evolves, demand paging continues to be refined and enhanced. Emerging trends such as machine learning, memory management, and adaptive algorithms are shaping the future of demand paging for even greater efficiency. Coming to the conclusion, demand paging in OS is a memory management technique used in operating system to optimize memory usage. Demand paging offers several advantages such as reduced memory usage, faster process startup times, and more efficient use of resources. Overall, demand paging is an effective technique for managing memory in modern operating systems. Demand paging plays a vital role in optimizing memory management. By understanding its benefits, challenges, and practices, organizations can achieve efficient resource utilization and enhance overall system performance. Thank you for watching this video.